Hi class, this is part 2 of section 5.3. Okay, so we're up to example number 5. We're going to state the domain of each function and then find vertical and horizontal asymptotes to the graph. So stating the domain, we've been doing this for a while now. We care about the denominator. So factor the denominator, in this case x minus 3 times x plus 3. We can't divide by 0. So the domain will be everything except for plus and minus 3. So in my head, I just said x minus 3 equal to 0 to come up with x equals 3. Same thing here, x plus 3 is equal to 0, so x equals negative 3. So those are the two numbers that must come out of the domain. Okay, next we want to check to see if our rational function can be reduced. Okay, so factor and cancel. So I factored the denominator, but nothing is going to cancel. Since nothing cancels, that tells me that the two numbers that came out of the domain are both vertical asymptotes. Okay, so the graph of this function would have two vertical asymptotes. The horizontal asymptote, to determine that, we need to look at the degrees of the numerator and the denominator. So we want to compare the degrees. Okay, so the degree of my numerator is 1. The degree of the denominator is 2. Right, so we're looking at these exponents here. So the exponent in the numerator is 1. So I have degree 1 over degree 2. So I have a higher degree in the denominator. Anytime that happens, the horizontal asymptote will be the line y equals 0. Okay, so that's again whenever you have a larger degree in the denominator. Okay, and I'm going to talk more about that as we move on as well. Okay, moving on to the second one, the domain of the function will be everything except for 7. I can see that this rational function is already in lowest terms. Okay, so that tells me that the vertical asymptote is this number that was eliminated. So the vertical asymptote is the vertical line x is equal to 7. Now for the horizontal asymptote, so this is where we compare the degrees. This time I have degree 1 in both. So the numerator is degree 1 and the denominator is also degree 1. When the degrees are the same, you compare the leading coefficients. So I have 3 as the leading coefficient in the numerator and 1 as the leading coefficient in the denominator. So the horizontal asymptote will be y is equal to 3 over 1 or 3. So y equals 3 is our horizontal asymptote. Okay, so I'm going to take a minute and explain why that's the horizontal asymptote. Okay, so let's actually go back to the one we just did, r of x. Okay, so the horizontal asymptote actually tells us about the end behavior of the graph. So we talked about end behavior when we talked about our polynomial functions. So the end behavior is what happens when x is very large and negative or when x is very large and positive. So in calculus, that's written as the limit as x goes to infinity if we're considering what happens when x is very large and positive. So if I have the rational function 2x over x squared minus 9, and I want to know what happens when x is very, very large and positive, so as x goes off to infinity, I can see in the denominator that subtracting 9 has very little effect over the denominator because I have this x squared first. So x is getting bigger and bigger and bigger. So x is a million or a trillion, and then you square it. So think about taking a number like 1 trillion and squaring it. You're going to get this enormous number. So taking 9 away from it is going to have very little effect over that number. Okay, so since I'm taking the limit here, I can disregard that minus 9 that's in the denominator. Once I do that, I just have 2x over x squared, so this can now be reduced. So I'm still taking the limit. I'm considering what happens when x is very, very large and positive. I'm going to reduce my fraction so it becomes 2 over x, because I had that x squared in the denominator, so the x's cancel. Okay, so x is getting bigger and bigger and bigger, but it's in the denominator. So I have 2 over a number like a million, 2 millionths, 2 billionths, right? 2 over a very, very, very large number. That ratio is going to go to 0. Okay, so that's why we have that the horizontal asymptote is y is equal to 0. Okay, the same thing would happen if I switched that infinity to a negative infinity. This would just change to 2 over a very, very, very large negative number, but still that ratio would go to 0. Okay, and now let's look at f of x. So again, I'm considering what happens when x gets really, really, really big and positive. So the limit as x goes to infinity of 3x plus 5 over x minus 7. Okay, so the same idea, I'm taking the limit as x gets really, 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 really big. So x is going off to infinity. So adding 5 to it doesn't change that number very much. 3x plus 5 is going to be a number very close to 3x if x is a million, right, or a trillion. So 3 trillion versus 3 trillion plus 5, you know, essentially very close to the same number, right? Same thing in the denominator. Subtracting 7 does not have much of an effect over this x value if x is a humongous number. Okay, so once I disregard those extra terms, I'm left with 3x over x, which we reduce. So those x's cancel, so it's just the number 3. So as x gets really, really, really big, what happens to the number 3? Well, nothing, right? It just stays 3 because it doesn't involve the x anymore. Okay, so that's why if the degrees are the same, we look at that ratio of the leading coefficients. So it wouldn't have mattered if this was 3x squared over x squared minus 7. These still have the same degree. We would still disregard the plus 5 and minus 7 for the same reasons we've talked about. 3x squared over x squared, as long as these degrees are the same, it would still reduce to 3. Okay, so that's why this is what we do anytime the degrees are the same. Okay. If the degrees are the same, look at the ratio of the leading coefficients. If you have a higher power of x in the denominator, okay, basically that x in the denominator is going to carry over. So you have 2 over a really, really, really big number, so that ratio goes to 0. Okay, for this class, I just want you to be able to find those horizontal asymptotes, okay? Understanding why it's the horizontal asymptote is gonna take a little bit of time, and you're gonna talk about this again in calculus, so in your next math class. Okay, but I just want to talk about it a bit so you get used to it and you understand a bit, hopefully, about why those are those asymptotes that we have. Okay, so moving on to the next one, capital F of x is equal to x minus 1 divided by 2x plus 6. Okay, so to find the domain, we factor the denominator. So the domain will be everything except for -3. The numerator can't be factored, it's just x minus 1. Nothing cancels, okay? So since nothing cancels, that tells me that the number that's been taken out of the domain will be a vertical asymptote of the graph. So x equals -3 is the vertical asymptote. Okay, next we have our horizontal asymptote. So for this we look at the degrees. Again, I have degree 1 over degree 1, so the degrees are the same. I look at the ratio of the leading coefficients. So 1 over 2. Therefore, the horizontal asymptote is y is equal to 1/2. Okay, so I still have this last one to do, g of x, but I'm going to get a new slide and we're going to go back to the beginning and kind of start again and go over these. Okay, so finding the domain of the function, factor the denominator. Whenever the denominator is 0, those numbers have to be out of the domain. Okay, so the domain cannot be plus or minus 3. Because my fraction was in lowest terms, the numbers that came out of the domain become vertical asymptotes. Okay, the horizontal asymptote, remember this you get by looking at the degrees. We had a higher degree in the denominator, therefore the horizontal asymptote is y equals 0. For the second one, determine when the denominator is equal to 0. Well, that happens when x is equal to 7. So x cannot equal 7. That's the domain of our function. Vertical asymptote, again, now we look to see if our function was in lowest terms, which it was. Nothing canceled. That tells me that x equals 7 will be a horizontal asymptote. Sorry, will be a vertical asymptote. The horizontal asymptote we get by looking at the degrees. Degree 1 over degree 1. So the horizontal asymptote is the ratio of the leading coefficients. So 3 over 1, which is 3. Okay, so the next one, the third one, factor 2 out of the denominator. And we see that x cannot equal negative 3. Again, my function was in lowest terms, so the number that came out of the domain becomes a vertical asymptote. So x equals negative 3 is our vertical asymptote. Horizontal asymptote, we look at the degrees, degree 1 over degree 1. So then look at the ratio of the leading coefficients. So we have y is equal to 1/2. Okay, so now for the fourth one that we have here, factor the denominator. This factors to x minus 3 times x plus 2. We were looking for two numbers multiplied to be negative 6, add to be negative 1. So we came up with negative 3 and positive 2. And we're ready to state the domain. So the domain is everything, all real numbers x, such that x does not equal 3 and x does not equal negative 2. Okay, so now be careful. After you do the domain, then you're almost ready to determine the vertical asymptotes. Okay, we have to go back to our function and see if it can be reduced. So now I'm going to factor the numerator. I have the difference of two perfect squares. This factors to x minus 2 times x plus 2. Okay, so this is different. This hasn't happened in the first three. Here, those x plus 2's will cancel. So I really have x minus 2 divided by x minus 3. This tells me, so notice I still have x minus 3 in the denominator. This tells me that 3 is, think of it as still causing a problem. So the vertical asymptote is when x is equal to 3. Okay, because x minus 3 is still here in the denominator. Okay, so that's going to be our vertical asymptote. When x is equal to negative 2, we get a hole in the graph. So there's a hole in the graph at x is equal to negative 2. Okay, so for our rational functions, so what we're looking at in these next two sections, 5.3 and 5.4, to determine the domain of the function, determine when the denominator is equal to 0. The numbers that were taken out of the domain, something's going to happen there, okay? But you don't know what yet. The two options for any number taken out of the domain is going to be a vertical asymptote or a hole in the graph. So you get a hole in the graph if it cancels. So x plus 2 canceled. So that tells me that x equals negative 2 is my hole. The other guy, x is equal to 3, did not cancel, so that's the vertical asymptote. Okay, next we're ready for the horizontal asymptote. We look at the degrees. The degrees are the same. It actually doesn't matter if you go back to the original or if you look at the reduced form. The degrees are the same. Degree 2 over degree 2 or degree 1 over degree 1, depending on where you're looking. Okay, the ratio of the leading coefficients is the same, still 1 over 1. Okay, so again here I factored the denominator first, and that'll tell me the domain. Then factor the numerator and see what cancels. In this case, x plus 2 canceled, so x equals negative 2 becomes the hole in the graph. So the other guy, x equals 3, is your vertical asymptote. Okay, so here's another one, kind of like what we were just doing. The domain, so start with the domain. So factor the denominator. I can factor out a 4. And then I'm left with x squared minus 1. So the 4 came out. And then we have x minus 1 times x plus 1. Okay, so the domain is everything, all real numbers x, such that x does not equal plus or minus 1. I took a 4 out as opposed to taking out a 4x If a 4x was factored out, then x could not be 0. Okay, but we didn't take out a 4x, just a 4. Okay, good. So remember now, something's happening in the graph when x is equal to 1 and when x is equal to -1. Something must be going on in the graph, but we don't know if it's going to be a vertical asymptote or a hole or one of each. Okay, we don't know yet. To figure it out, we then have to go back and factor the numerator. Okay, so let's factor 3x squared plus 2x minus 1. So I want two numbers multiplied to be -3, add to be 2. So 3 times -1 will work. Rewrite the middle term, so 3x squared plus 3x minus x minus 1. Factor out the 3x. The last two guys, we can factor out a negative. This way the x plus 1's match up. So our numerator factors to x plus 1 times 3x minus 1. Okay, so we notice that these x plus 1's cancel. Okay, if x plus 1 cancels, then x equals -1. That's what would make this guy 0, right? If I plug a -1 here for x, I have -1 plus 1 or 0. This canceled, therefore when x is equal to -1, that is going to be the hole in the graph. X minus 1 is still here when I write my function in lowest terms. So x equaling 1 is going to be the vertical asymptote. Okay, the horizontal asymptote, this we get by looking at the degrees. You could do this either back in the beginning. Way back in the beginning, we had degree 2 over degree 2. So our horizontal asymptote is going to be the ratio of those leading coefficients, so 3/4. We would get the same answer if we looked here at the end. This is degree 1 over degree 1, but the ratio is still 3/4. Okay, good. Another option that could happen, so let me just explain it real quick. So this is some new function, f of x. Let's say we had 3x to the 3rd power in the numerator and then just an x squared in the denominator. So notice here the degree of the numerator is bigger than the degree of the denominator. Okay, if this is the case, then there is no horizontal asymptote. Okay, we're not going to look at functions like this. They don't come up in your next math class either, so they don't come up in business calculus. But I just wanted to mention that this is another option if the degree of the numerator is more than the degree of the denominator. In this case, it's more by exactly 1. That gives you what's called a slant or oblique asymptote. If it's bigger by 2 or 3 or 4, then you have what is called a curvilinear asymptote. Okay, that's actually on a later slide, but we're not going to be looking at examples of that. I just wanted to mention it. Okay, this one I think I have graphed for you just to give you an idea. We're not graphing until the next section, but I wanted to show you what it looks like to have a hole in the graph. Okay, so again, going through the steps, factor the denominator first to get the domain. Okay, then cancel, and you can figure out, this way you can figure out of those numbers that are taken out of the domain, which is going to be a horizontal asymptote and which is going to be a hole. Okay, so here's the graph of the function. Again, we're going to be doing this in the next section, but I just wanted to show you here. So I have my vertical line, x is equal to 1. That's my vertical asymptote. Horizontal asymptote, y equals 3/4. And then I knew there was going to be a hole in the graph when x was equal to -1. Okay, but you still need to know the y value of the hole, because literally this is a point that goes on the graph. Just instead of being a closed circle on the graph, it's an open circle on the graph. Okay, to get the y value for the hole, and you're going to need this in the next section in 3.4, what you want to do is go to this reduced form of your function. So after you factored and canceled, go to that reduced form and plug in the x value. Okay, so the graph has a hole when x is equal to -1. So we're going to plug in -1 for x into our reduced form. So that's what I did down here. So 3 times -1 minus 1 gives us a -4 in the numerator. I plugged in a -1 for the x in the denominator. -1 minus 1 is -2. multiply, so we have -8, so we'll get 1/2. So the whole, or the open circle, is when x is -1 and when y is 1/2. Okay, so it gives, in terms of your graph, it gives you information on the graph. So here's the hole, so you know the graph has to kind of pass over that hole. It jumps over it, but it still gives you information about the graph. So that's what it looks like to have a hole in the graph. Okay, horizontal asymptotes. So I just wanted to write out what I've been saying, okay? We look at the degrees. So a rational function, this is just a polynomial over a polynomial, okay? They're just kind of written out this way since we don't know what the degrees are. So we're using n and m. So n is the degree of the numerator, m is the degree of the denominator. If n is the smaller number, so if m is bigger, if you have a bigger degree in the denominator, that's when the horizontal asymptote is y is equal to 0. Okay, this is also called a proper rational function. It's similar to a fraction. If we have the fraction, say 5/12, this is a proper fraction because the denominator is bigger. If you had something like 4/3, this is improper, right? Because you don't want the numerator to be bigger. It's considered an improper fraction. Okay, so same thing for rational functions. If the numerator has a higher degree, it's considered improper. So proper would mean denominator has a bigger degree. In that case, y equals 0 is the horizontal asymptote. Okay, so otherwise, the degree of the numerator is either the same or bigger. So we looked at examples where the two degrees were the same. When the degrees are the same, you just want to look at the ratio of the leading coefficients. So what are the numbers that go? The leading coefficient is the coefficient of the x with the highest power. Okay, so just whatever these leading coefficients are. That'll be your horizontal asymptote. Okay, these other two cases are not going to come up in our class, but just to mention them, if the degree of the numerator is bigger by exactly 1, you get what is called a slant or oblique asymptote. If the degree of the numerator is bigger by 2 or more, you get what is called a curvilinear asymptote. Okay, if you're interested, you can come and talk to me during office hours, and I can give you examples of functions that have either a slant or a curvilinear asymptote. But this would be simply if you're interested in learning about it, because it's not going to come up in our class on a test or anything, and it does not come up in business calculus either. Okay, so this is what you guys need to know. When do we get a horizontal asymptote? Okay, when is it y equals 0? When is it the ratio of the leading coefficients? Okay, and then also when do you not have a horizontal asymptote? Okay, so in our cases, horizontal asymptotes, degree of the denominator is bigger, or the two degrees are the same. Okay, otherwise you don't have a horizontal asymptote. All right, these are the 3 examples that you're going to complete and turn in to me through Canvas. For these 3 functions, start by stating the domain of the function, and then find the vertical and horizontal asymptotes. Good luck. Let me know if you have any questions.